continuing it, durability of concrete. We will look into some more degradation processes, that is chloride ingress, corrosion and alkali aggregate reaction. But however, we stopped yesterday with carbonation. So, we will have some discussion on carbonation as well. So, anyway, general outline of this lecture therefore would follow. We will discuss some issues of carbonation, which we actually left inconclusive in the last lecture, look into chloride ingress and resulting corrosion from both carbonation and chloride ingress process. Then we will look into another degradation process called alkali aggregate reaction in today's lecture. So, let us continue with the carbonation process which we have seen yesterday. If you recall that we actually were discussing about the carbonation process, where we said the carbon dioxide from the atmosphere can penetrate into the concrete, right, because carbon dioxide is just present in the atmosphere and it can enter into the concrete, right, and through the pores that is there, through the surface it will enter, and in presence of moisture this carbon dioxide, which will diffuse into the air filled pores, the chemical reaction of calcium, it will react with calcium hydroxide that is present as a hydration product of cement and form calcium carbonate and water. Now, this process all takes place in presence of H2O, it takes place all in presence of H2O. If there is no moisture, the reaction does not go on. And if you recall again, then we said that this process, since it consumes all the calcium hydroxide and alkaline material in concrete, the pH gets reduced below 9. This one important point is that carbonation process do not continue in completely dry concrete, nor does it continue in fully saturated concrete, because it requires presence of moisture, and also in completely saturated condition, when it is all pores are filled with water, the carbon dioxide will not be available. So, this point is important and we should recall this. Now, carbonation front, as we call it, it progresses from surface to inside, surface to inside. For example, here is the carbonation front here, and this is our pores, and this is moist here, moisture film here and air here when carbonation can proceed. So, this is just recalling from whatever we have discussed yesterday. Now, following from there, if we look at it, how do you protection against carbonation? You see, first thing is presence of moisture and air, both are necessary for carbonation to progress, progress. Water saturated concrete exhibit lower rate of carbonation. Anyway, so condition should be such that we should actually see that there is no moisture penetration into the concrete. And then service life with respect to carbonation is the time when carbonation front reaches the river level, because we said we have, if you recall, when we defined the service life with respect to corrosion, we said that first there is a period which we call depassivation period, and during this depassivation period the carbon dioxide from atmosphere will enter into the concrete, and pH at the reinforcement bar level will get reduced. When carbonation front reaches to the reinforcement bar level, that is the time when we call it the service life. Depassivation has taken place, and that is what is the service life with respect to carbonation. And if we recall back again, we said that some of the oxides formed during rusting process, they are not very dangerous, because their density is relatively high, nearly as high as that of the steel, and therefore they do not cause volume expansion, and all these oxides which are not so dangerous, they form passive films, and this passive film formation takes place only at high pHs, sufficiently high, and carbonation actually reduces down this pHs, and therefore the passive layer formation which has taken place, that gets broken and depassivation takes place. So, therefore, service life with respect to carbonation we define like as, if you remember from this diagram, let me just redraw it. It was something like this. this is this one and this is. So, we call this as Tp, and Tp when this time is Tp, this time is the depassivation time, and this is the time when the carbonation front has just reached the reinforcement bar level. So, it starts from the surface and gradually reaches up to the river level, and that is what we call as service life with respect to carbonation, right. Okay. Best way to protect concrete or reinforcement bar against depassivation due to carbonation is to have an impervious surface concrete. Surface concrete should be impervious, or in general total concrete is made actually at the moment we make the complete concrete impervious. And how do we make it? By lower water cement ratio, and also we provide adequate cover depth such that carbonation take large time to reach to the river level. Okay. This is what is with respect to carbonation. Of course, cracked concrete at the point of crack, if the crack has gone up to reinforcement, it will quickly get carbonated, and there are other detailed issues related to carbonation. Wetting and drying actually influences the carbonation time or service life with respect to carbonation. Such issues we will not discuss here, but these are the issues, relevant issues also one can look into. So, for our purpose we understand that carbonation is a phenomena which actually does not create any problem to the concrete, but it can lower the pH at the reinforcement bar level by when the carbonation front progresses from surface to inside through the depth of the concrete, and when it reaches to the river level, depassivation can occur. So, we have to prevent the depassivation, and therefore, impervious low water cement ratio concrete is a useful solution to make that. Of course, you can put many other covers, but it has to be cost effective also. Now, next way how depassivation takes place is the chloride ingress into concrete. Now, as I mentioned earlier that chloride and carbonation, they are not really much of a problem as far as concrete is concerned. It does not change the property of the concrete, nor its strength gets reduced or anything of that kind, but they affect the rebar, reinforcement bar, the steel which we put as reinforcement in concrete, because their corrosion can be initiated if sufficient chloride has gone in. So, this is also related to Tp. This is also related to Tp. Now, let us distinguish two situations. One is what is saturated concrete. Now, we are looking at external ingress. So, we are looking into chloride ingress, external chloride. There can be chloride coming from the ingredients themselves, which of course, we should not allow, but that is we call as internal concrete. But that is if a good quality control is there, normally such chloride should not be present. But we will discuss about that somewhat, a little bit about that also sometime later. But let us look into a situation. Your concrete is in chloride environment, let us say somewhere in the marine environment, in contact with the chloride water, and the concrete is likely to be saturated in such situation, and there this insaturated concrete in completely submerged marine structure, let us say, the chloride can enter into the concrete, because this is fully saturated. So, there is all water inside. Now, concentration of chloride here will be low compared to concentration of the chloride outside, where you have got a lot of all chloride solution is there. So, chloride ion can penetrate into the concrete, chloride ion can penetrate into the concrete due to concentration gradient. We know that when a concentration gradient exists between two locations, that is, if there is a delta C is a concentration difference between 2 points, and the distance between them is delta x, then delta C delta x is nothing but concentration gradient, and Fick's law states us the flow is proportional to some diffusion coefficient into dC by dx, where q is the rate of flow of this ion per unit area per unit time into some diffusion coefficient multiplied by concentration gradient. So, when it is saturated, this can, because there is a concentration gradient existing, there is a high concentration of chloride here, low concentration of chloride here, and it is all saturated, all water is there. So, chloride ion will diffuse from this side to this side. This is the phenomena, molecular diffusion, this is ionic diffusion. Of course, this phenomena is still more complex than what we are simply defining through this fixed diffusion equation, but let us understand physically. Since there are high concentration of chloride here, less concentration of chloride here, so chloride can diffuse from higher concentration to lower concentration, and the process of chloride ingress into the concrete will be through process of diffusion in saturated concrete, right. Let us see what happens if we are looking at another situation of unsaturated concrete. In case of unsaturated concrete, the phenomena would be slightly more different, because here you see in unsaturated concrete, partially saturated concrete, something like splash zone in marine structure, where wave hits and there is alternate wetting and drying, or foundation in contact with chloride, contaminated groundwater, above the lowest groundwater level and below the highest groundwater level, and so on. So many places this situation one can come across, where the concrete remains partially saturated, not fully saturated all the time. In a submerged situation, it is fully saturated all the time, but in places where wetting and drying goes on, it is partially saturated, because sometime the liquid or the solution will enter into the concrete, and then sometime later it will dry off. So in such a situation, the flow through partial or partially saturated concrete takes place, and in partially saturated concrete, both the phenomena will actually contribute to the chloride ingress. First of all, chloride ingress with the solution would take place. That means some solution goes inside. Since the solution contains chloride, some amount of chloride will enter into the concrete with the solution, because there is solution. So solution goes and it contains chloride. So some solution solution itself will bring the chloride, and that is quite significant amount, possibly much more than the diffusion component. Now solution itself will carry some amount of chloride, right. As the saturation increases, chloride concentration inside the concrete will also increase. Now when it dries off, let us say a situation of wetting and drying, when it dries off, the moisture or water will get vaporized and moisture vapor will get out. What about the salts? Salts will remain deposited there. So again the solution ingress takes place, some more chloride will go in. So in partially saturated situation, wetting and drying can result in very high level of chloride concentration. Now since there is even when it is partially saturated state, some pores and some portion of the pores are filled with solution, which will have a lower concentration than outside. So diffusion process can also take place. So in partially saturated concrete, both diffusion and solution ingress both contribute to the chloride ingress, overall chloride ingress, and the chloride front might enter depending upon the situation, right. Now when the chloride in the concrete reaches a particular value, a threshold value or some critical value, then we say that depassivation can take place. Just some amount of chloride entering into the concrete, very little amount of chloride entering into the concrete may not initiate depassivation, but at some level of the chloride concentration, depassivation can start. Okay, we some critical level. Sometimes it is referred to as threshold chloride level. But let us understand something more about this chloride. You see, the chloride that is present in concrete, if I want to find it out, I will actually take out some portion of the concrete, grind it and dissolve it in either water or in acid, concentrated nitric acid, right. So there are two types of chloride one can distinguish: water soluble chloride and acid soluble chloride. So when I dissolve it in concentrated nitric acid, you see, when I dissolve it in concentrated nitric acid, this is acid soluble chloride, which actually I dissolve it in concentrated HNO3, and this is simply in water. So I dissolve it in concentrated HNO3, that we call as acid soluble chloride, and it has been observed that acid soluble chloride is more than this. This is greater, this is greater than this is more compared to water soluble chloride. What does it mean? Some of the chlorides present in the concrete do not go into water solution, don't get dissolved into water, and some chlorides get dissolved into water, right. And therefore we distinguish two types of chlorides: total chloride and free chloride. Free chloride are the ones which are water soluble. and actually they can contribute to the corrosion reaction process, whereas the total chloride, in totality they do not contribute, but they can think, one can think them as a potentiality of contributing to the free chloride. So, there are two types of chloride, total chloride and free chloride, and difference between them is what is bound chloride. So, you can have some amount of bound chloride present in concrete, and this bound chloride is bound both physically as well as chemically. We shall see this a little bit later on. So, depassivation actually takes place when chloride levels reaches a critical value at the rebar level. Quite often it depends on cement and steel type as well. Different types of steel might have different depassivation levels of chloride. One idea was that chloride to hydroxyl ion ratio should be greater than 0.6. Well, but it would also depend upon type of cements, because there are several varieties of cement, blended cements which have come, and their chloride binding, their reaction to chloride situation is different than the earlier ordinary Portland cement. It may be this critical chloride level may also depend upon types of steel, because we have now varieties of steel actually available. We shall discuss those about steel sometime later on, but so therefore it depends upon all that, right. So, depassivation takes place at above some threshold level, and then service life therefore we define with respect to above depassivation. So, when the chloride level has reached to such a level, such concentration that depassivation of the steel occurs, that time we call as a service life. So, depassivation has to occur. Now, it usually has been defined in terms of chloride concentration, but if so far it has usually been defined in terms of some chloride concentration. But one thing, the intensity with which chloride actually causes depassivation, or the level or the critical level, as far as the codes are concerned, allowable chloride level in concrete, this has been reducing from time to time. Earlier whatever 1950s, whatever the allowable chloride level in concrete, and today's allowable chloride level in concrete, in most of the codes of practice you will find that there is a reduction in this value. So, because it is a complex phenomena, its understanding is still developing. So, but we have certain values which we will look into later on. Now, service life therefore we define with respect to depassivation. When depassivation chloride level has reached to such a level that depassivation occurs, that I call a service life with respect to chloride. Now, let us come to internal chloride. When you have internal chloride, that is, it has come from ingredients. Chloride can come from ingredients, it can come from outside also. Outside I mentioned was in marine environment, or groundwater contaminated with chloride. Of course, in western world they use de-icing salts, because there is freezing during the winter, and they use what is called de-icing salts, and these de-icing salts used to contain a lot of chloride, and this chloride would penetrate into the concrete and cause corrosion of rebar inside. So, de-icing salts problem has actually created chloride induced corrosion in western world, in North America and Europe, but internal chloride comes from the ingredients, and that you have not tested if you have not tested the ingredients properly. For example, if the water that you are using, especially the groundwater from deep groundwater source, that may contain a lot of chloride in arid, semi-arid or composite monsoon type of climate of northern India, because if you are using groundwater, that may contain a lot of chloride. Then marine environment I have talked about, but chloride may also come into the internal, like marine, close to the marine environment. If you use the water, sea water, that can also bring in chloride. So, internal chloride can come from water, is one of the biggest source. The second source could be the sand, particularly if you are using land quarried sand. Now, this land quarried sand is not thoroughly washed, and it will contain a lot of soluble salts. If it is thoroughly washed, then of course soluble salts go away, and therefore chloride also goes away. River sand would usually contain much less chloride, because soluble chloride should have been washed away by the river itself. So, internal chloride can also be present if the quality control or was not proper, one did not check the water quality before putting it into the concrete, and this can lead to severe problem, because you can have, if you have sufficient quantity, your TP, that is your TP can be simply 0, TP, that is depassivation time, can be 0. So, from the first day onwards you can have initiation of corrosion right from the beginning. Only problem is you have to have only additional thing you need is the presence of water. So, if your quality of concrete is not good and you have used groundwater which contains lot of chloride, in very short time you can see corrosion distress may be may be visible, right. Now, that is why IS code, Indian standard codes, have actually restricted the total chloride in concrete 0.4 and 0.6 kg per meter cube for pre-stressed concrete. This is for pre-stressed concrete and this is for reinforced concrete. So, in reinforced concrete you should not have more than 6 kg per meter cube of chloride in total chloride. So, this is acid soluble chloride, you should not have more than that in internal chloride. This can be avoided, easily avoided. Internal chloride can be easily avoided by testing the water, the aggregates, etc. Usually chloride bearing admixtures are not used much today because of the reinforcement corrosion problem. So, this is what is internal chloride, and external chloride we have just discussed, right. Now, how do I protection against chloride index, chloride ingress? Some of the total chloride remain physically bound and chemically bound with the cement, that is what I have mentioned. So, this issue is important. And how does it get chemically bound? You see, C3A in cement reacts with the chloride. Now, chloride may be in form of sodium chloride, but it will react with calcium hydroxide forming calcium chloride. Now, this calcium chloride reacts with C3A and then forms what is known as Friedel salts complex, 3CaO, Al2O3, this is called Friedel salts, or other kind of calcium aluminate chloroaluminate salts, calcium chloroaluminate salts. You see, C3A is the most reactive compound in the ordinary Portland cement. So, it reacts with so many things, like it reacts with sulphate, it reacts with also chloride. Usually you will have sodium chloride present, usually you will have sodium chloride present, sodium chloride, this will react with calcium hydroxide, giving rise to calcium chloride plus sodium hydroxide, So, or any other form of chloride, they will react with calcium hydroxide. So, you will have calcium chloride and this reacts with C3A forming what is called Friedel salts. This forms calcium chloroaluminate and hydrates, and this is what happens, right. So, therefore, when this forms, this is not water soluble, this is not soluble, this remains chemically combined, does not come into the solution, this remains chemically combined, this does not come into the solution. So, this is chemically binding, chemically combined, right. Now, here you see, if you have higher C3A, more bound chloride you will have. Some chlorides also get physically bound to the surface of the gel structure, physically bound, adsorbed at the surface. So, in totality, the bound chloride consists of both physically as well as chemically bound chloride. Now, here you see slightly different. In case of sulphate, high C3A would cause sulphate attack, a tringite formation. In case of chloride, of course, high C3A would mean that you will have lot more binding capacity, and that is why sulphate resisting cement is not good in marine environment, because you have both chloride as well as sulphate. So, where you have both chloride as well as sulphate, if you use low C3A, then chloride binding will get reduced. If you use high C3A, sulphate attack would be more. So, therefore, that is why sulphate resisting cement is not good in marine environment. Okay. So, that is what is chloride binding. Now, what should I do then? I should have impervious surface concrete, that is the first fundamental. You see, always carbonation or chloride ingress, acid attack, sulphate attack, all cases moisture comes in. In some cases also carbon dioxide comes in. So, in all situations actually I need an impervious surface concrete, because the surface through which all this fluid attacking fluid or those chemically aggressive fluid comes in. Therefore, I must make the surface impervious. You can put a coating, all right, but that would be costly. So, by and large the concrete itself would be made such that its surface is impervious. Lower water cement ratio therefore is the solution, always a solution, and adequate cover depth. Now, here as far as chloride is concerned, PSC, that is Portland slag cement, and Portland pozzolana cement also improves the protection. So, they improve the protection by both means. This can improve the protection to all concrete by improving the permeability or improve the imperviousness, which we have seen earlier, because we said when we were talking about the hydration of pozzolana, which hydration of cement and pozzolana etc., we have seen that additional CHS structures, CHS are formed at the cost of calcium hydroxide. Calcium hydroxide reduces and lot more gels are formed, and the pores would be segmented more, or there will be less even. Totality porosity would reduce when you use slag or fly ash or similar other pulverized fuel ash in cement, or use blended cement. So, therefore, imperviousness is the first thing which improves, they improve. That would actually protect carbonation also, but here it does additionally, because the chloride binding of PPC is more, PSC is more, they will be they can bind also chloride more, and they provide impervious surfaces. So, therefore, putting all together, this type of cement also shows better performance against chloride in this. Now, chloride and carbonation is not a problem, as I said, they only initiate corrosion process. So, let us look into the corrosion process. You see, corrosion process of rebar in concrete is an aqueous corrosion, and it can be well described by this diagram. This is our rebar, this is the rebar, and some it is an electrochemical process. It has been understood that aqueous corrosion is an electrochemical process. So, rebar corrosion is an electrochemical process, after all metal. So, it can give away some electron, it forms generally electrovalent bond, and therefore, where it loses, metal loses electron, and also this its metallic bond structure is responsible for its being good conductor of electricity, etc. So, metal can lose electron very easily. So, therefore, reactions of metal usually takes place with charge transfer, can take place with charge transfer. Now, where electrical charge transfers are involved, such reaction we call as electrochemical reaction. Now, corrosion of rebar in concrete is also an electrochemical reaction, and in such electrochemical reaction you must have an anode, and also some portion somewhere you should have a cathode. If you remember your electrolysis, then you would remember there used to be an anode, cathode, and electrolyte, and the anode and cathode are externally connected. Anode and cathode are externally connected. Anode, if this is my anode and this is my cathode, they will be externally connected. They will be externally connected by some connected. They will be externally connected, so that current can pass through. That is the circuit of a battery, right. So, here also I have anode and cathode, but anode and cathode are there in the same bar. Some portion of the bar will act as anode, some portion will act as cathode, because there are non-uniformities. So, the potential, or in other words the capability of losing electron is more somewhere, or losing iron, positive ion is more somewhere, right, in compared to somewhere more compared to some other places where it may not lose or allow metal dissolution. Here the anode and cathode are there in this bar, because there is non-uniformity, physical as well as chemical non-uniformity in the bar itself. Some portion will form as anode, some other portion will form as cathode. So, in the same bar you have anode and cathode. Whereas the electrolyte is the pore solution outside. So, the pore solution outside, concrete pore solution outside form as an electrolyte, and then you have external connection for carrying the current in case of an electrolytic cell. Here this itself carries from anode and cathode are internally connected to the rebar itself. So, in other words, you have a circuit completed like this as shown. So, what happens at the anode, metal get dissolved into Fe, iron, since we are dealing with iron, Fe++, 2 electron. So, it loses 2 electron metal and goes into solution. This electron moves towards the cathode, and at cathode it actually moves into the solution reacts with water, important, and also oxygen, forming hydroxyl ion. Typical cathodic reaction, an anodic and in anode metal dissolves, and this hydroxyl ion then moves this side, right, to some side, and then reacts with the Fe2++, forming this product. Now, this product is not stable. Depending upon the complete environment, you might have formations of FeO, Fe2O3, Fe3O4, Fe3O4, or FeOOH, H2O, which I mentioned yesterday, something like this, or FeOH3, whatever it is. There are several possible reactions are possible, and this I said was red rust, all this I said was black rust. So, I said this, this I just gave example of black rust and red rust yesterday, and black rusts are not problematic, red rust is problematic because it expands in volume and causes pressure into the concrete, which eventually cracks. So, now the corrosion process therefore is an electrochemical process, but 2 points I would like to highlight here, that is I require H2O and I require oxygen. So, presence of electrolyte, anode, cathode, the connecting rebar, this is automatically provided by the rebar itself acts as this connector, anode and cathodes are there in the rebar themselves. Only thing that should come from outside is water and oxygen. So, in presence of water and oxygen, this process, corrosion process, can start and go on. Now, if you have high pH, if the pH is high, then black rust formation takes place and it remains depassivated. Only when pH is low, this depassivated, at high pH it is passivated, at high pH it is passivated, it remains passive, it remains passive at high pH, it remains passive at high pH. So, passive, it remains passive in high pH. At low pHs it gets depassivated. This is one form, and then corrosion can proceed. The other situation is when chloride, other situation is chloride, so this is one high pH. So, low pH and or low pH it gets depassivated, right, depassivated. So, that is important, at low pH it gets depassivated. Okay. So, low pH it gets depassivated, right. The second way that this reaction, this passive layer over the bar can get depassivated is due to chloride. Now, what does chloride do? Chloride, when it is sufficient in quantity, when chloride quantity is sufficient, it can, chloride quantity is sufficient, actually it will react with this Fe. So, chloride reacts with this, chloride reacts with this, chloride ion reacts with this, forming ferric chloride, chloride compounds, chlorides of iron, and these chlorides are not stable. So, they get broken down and chlorides remain free, but Fe goes and forms red rust. So, when you have sufficient chloride, one of the theories is that sufficient chloride, it can break the passive layer, it can destroy the passive layer, attack the Fe and reacts with Fe, attacks and reacts with Fe, forming chlorides, iron chlorides, Fe chlorides, but which are not stable. Now, these chlorides then break down and Fe reacts with oxygen, water, hydroxyl ion, etc., forming red rust, whereas chloride is again free to go back and attack some more Fe. So, in this process chloride does not get consumed, chloride is not consumed, but Fe is consumed to form red rust. So, chloride attacks iron, forms some compounds which are not stable. So, chloride actually attacks, chloride attacks Fe, forms this sort of compounds not stable, and then chloride is free again. Fe forms red rust, Fe forms red rust. So, you can see chloride in sufficient quantity, can really cause problem, if it is in sufficient quantity, because it does not get consumed itself, but continuously go on processing, producing red rust. So, this is the phenomena of reinforcement corrosion, right. So, this is what the basics of reinforcement corrosion in nutshell, and let us see what happens next, what is its effect. Now, when this is happening, corrosion process is happening, both oxygen and moisture is necessary. This is the first thing we have stated, that this is necessary, and therefore, completely dry or fully saturated concrete do not exhibit rebar corrosion. So, first thing is it must be moist, oxygen must be available, and if both of them are not available, then of course, corrosion cannot proceed. So, if you can protect the concrete, reinforced concrete structure against water ingress, corrosion will not progress. Oxygen, of course, you can't stop. If the pores are there, oxygen will always be present, but water moisture ingress can be stopped, right. Also, since the current flow has to take place through the concrete, resistivity of the concrete plays a strong role. High resistivity concrete obviously will show lower corrosion rate. Tendency of corrosion is always there, because iron Fe is not stable. Fe is stable only in combined form, in Fe, FeO, etc., oxide, sulphide, etc. Fe is always stable in combined form, but it is not stable just as Fe, because in nature it is not available. We produce it at the expense of energy. Therefore, tendency of corrosion will always be there, but we can control the rate, and resistivity of concrete plays a role there, or you keep it dry, no moisture comes in. So, there will be no corrosion, although iron given an option, given a chance, iron will corrode. Now, what are the effects of corrosion? Effects of corrosion are something like this. You see, the first step when corrosion process progresses, what will happen is, this is the steel bar, and this is the layer around, this is the bulk concrete, and this is the layer around the steel bar, and this is somewhat, because of the wall effect, etc., this bond area, the interface, again interfacial zone between the steel bar and the concrete, that will be somewhat porous zone, poorer concrete, because of wall effect, shrinkage and similar things which we have discussed several times, this will be somewhat poor, like aggregate surface. Now, when corrosion product starts accumulating here, if the product occupies more volume than the original material, then it will try to expand, and therefore, it causes expansive forces, forces outward forces, because it is trying to expand, trying to occupy more volume. That is why black rust is not so dangerous, red rust is, because red rust occupy 3 to 4 times more volume than the original steel. So, it dissolves some amount of the metal, same amount is now converted into 4 times volume. So, when there are 4 times volumes, it will exert radially outward pressure, and eventually, if this is your cover depth, it will crack, there will be cracks on this direction. So, this is called general corrosion. Usually throughout the structure, if this is occurring, then this sort of cracks are usually observed, but there is something more dangerous is known as pitting, where locally the reinforcing bar may be consumed with a large cathode area, anode area being very small. In such situation, loss of the metal could be also important together with such cracks, because such cracks may not be visible being in just one isolated place or 2 isolated places, but the loss of metal can result in serious problem, particularly in prestressed concrete and structures. So, if the loss of metal becomes so much that it fails, then if it is in a critical location or critical component, it can even initiate collapse of the structure. But they do give you signal much earlier, particularly this sort of general corrosion will definitely give you a lot of signal before failure, and therefore, one has to maintain it, repair it, even if it has occurred. First of all, one has to prevent that it does not occur, but even if it has occurred, one can repair it easily, right. So, now if you see the effect of corrosion further, we will see that this is what will happen in case of general corrosion in most of the places. For example, if you look at beams, the first stage you will see some crack parallel to the reinforcement bar. This is your reinforcement bar, you will see cracks parallel to the reinforcement bar on the both direction, and eventually concrete will fall off. In slabs, of course, the cracks developed in this manner, then there will be sagging of the bottom portion, and eventually the concrete will spool up, leaving the reinforcement bar exposed. That is the green ones are the reinforcement bar. So, this is the effect of corrosion, and you want to see a real life picture, we can just show it. So, usually quality of concrete in the covercrete, that is the cover concrete, modulus of elasticity, that is important, because you see what is happening is there are two-fold effect. First of all, concrete cover should be good and sufficient. There should be, it should be good and it should be sufficiently thick also. If it is sufficiently thick, first of all depassivation time itself will be longer if it is coming from outside like carbonation or chloride. Secondly, the cover will also provide protection against cracking, because if it has to crack, when the crack has to appear, it will take longer time because you have more material there. So, cover plays both roles, it should be good as well as its thickness should be adequate. Now, why higher elastic modulus? You know, tensile stresses are generated because of the pipe bursting situation. You know, we have seen the rebar pressure is exerted all in radially outward direction. So, if radially outward pressure is generated, then the stresses that is developed in concrete will be a function of elastic modulus, and it will crack only when the stress generated by such expansion is more than the tensile strength of concrete. So, modulus of elasticity of concrete, tensile strength of concrete plays a role. Higher tensile strength will obviously delay the cracking, higher modulus of elasticity will make, you know, stresses transferred will be relatively less. So, good quality concrete, cover concrete is very important, and adequate cover is also very important, you know, is the primary requirement together with protection against moisture ingress. This is most important. The moisture should not come into the concrete, because if moisture comes in, corrosion process can set in. If you have no moisture, no water, no oxygen, no corrosion. So, that is very fundamental to protection of corrosion. Use of blended cement improves this protection. Although, you know, it may be said that it consumes a lot of calcium hydroxide. So, there may be something happening to its pH may be lowered, although clear cut evidences along that line is yet debated. But anyway, what this blended cement does is they make it impervious, they make concrete impervious, and therefore, water penetration is much less, chloride ingress will be less. Besides that, they increase the resistivity of the concrete, and thereby they provide good protection against corrosion, but only when your concrete quality is good. If you make a bad concrete, non-engineered concrete, you use any cement, it is not going to serve your purpose. First thing is these issues, I should have good quality concrete with good elastic modulus, tensile strength, etc., and protection against moisture ingress, then all other thing would be good. There can be corrosion resistant rebar is another way of by which you can protect. Coating and surface treatment of concrete is one way of protection against corrosion. Coating of rebar, but cost has to be seen. There are fusion bonded epoxy coated rebars, there are other kind of rebar coating. So, you are actually creating a barrier between the rebar and the electrolyte, that is what you are doing. Inorganic coating of the kind of galvanization could be also there. So, there are varieties of coating of reinforcement bar is possible. So, you create a barrier between them. Of course, some of them can reduce down the bond strength between the concrete and the steel, but if you know how much is the loss, you can design accordingly. So, that is not a problem. Surface treatment of concrete are the other solutions. Now, surface treatments may be costly, it would depend upon the situation, environment, what environment you are working on. There are something called corrosion inhibitors, which you can put into the concrete and they will stop either the anodic reaction or the cathodic reactions. Sodium nitrites, molybdates, there are some of those. There are other kind of inhibitors also available, both anodic and cathodic inhibitors are available, but their use is not very, till date they are not, they are not very extensive use has been made of them, because they are all side effects and everything is not, one is not sure about, but these are also some other solutions. Cathodic protection, where electrochemically you protect the reinforcement bar by applying either an external current, impressed current, such that it will oppose the corrosion current. A second way is to have what is called a sacrificial anode. Now, such anode is connected to the reinforcement bar, and it is the metal is chosen in such a manner that it will always be anodic compared to iron. So, it will get dissolved, iron will be protected. Well, details we will not discuss about, but cathodic protection are other measures. Then there are some other electrochemical measures like you can actually remove chloride from the concrete by a process called dechlorination, or you can increase the alkalinity of concrete by alkalination and things like that. So, these are also electrochemical processes. Some of them are costly, not yet tried. There are problems involved with maintenance, because cathodic protection you have to monitor it continuously, but those are definitely some of those means of protecting. Now, this is the example of real life example of corrosion in a slab, real life example of corrosion in a slab. So, we have seen corrosion protection, and let us see what happens if you have not really taken care of it in the right time. And this is real, not coming from anywhere in the sea coast, but coming from composite monsoon climate of Delhi, mainly because ingredients were not properly tested. So, all protection measures stated, I would like to emphasize on the fact that corrosion essentially, many places we can avoid corrosion if we have good quality control of concrete, adequate cover, cover depth, depth of the cover. I should have adequate depth of the cover. Most of the cases in real structures, depth would be very, very small. Quality of concrete is a casualty, especially in non-engineered concrete, where it is all mixed manually and things like that. So, concretes which were concrete structure, many building structures particularly constructed in 1980s and even 90s, which are manually constructed, the quality control is bad. If you do not test the ingredients for chloride, in this particular case chloride came from the ingredients. So, if you do not test the ingredients, this can lead to corrosion. So, effect of corrosion real life situation could be something like this, but first fundamental is the quality of concrete, quality of cover concrete, and stopping the ingress of moisture, right. So, this is what is all about corrosion. Let us see now into the another degradation process called alkali aggregate reaction. Now, this occurs with certain types of aggregates. Active silica constituent in aggregate, there are certain active silica, and when they are present in aggregate can react with alkali present in cement. So, active silica and alkali present in cement, the always sodium hydroxide and sodium oxide and potassium oxides, these alkalis are present in cement. They are present as fluxes in the cement. So, because they bring down the burning temperature of the cement, So, therefore, they are present in cement always. Now, this alkali can react with some active silica, some of them if they are present, and they can result in what is known as alkali silica reaction. Now, this reactive forms of silica are, some of them are opal, this is the mineralogical name, minerals, opal, chalcedony and tridymite. These are some of them. If they are present, they are active silica, they may they occur in several rocks. So, they can cause this alkali aggregate reaction, right. This ones readily forms their hydroxides, because they are present in cement. So, they readily form their hydroxides and reacts with this siliceous material, forming alkali silicate gel. Now, this alkali silicate gel actually is voluminous in nature, they occupy more volume than the original reactants, and therefore, they exert pressure around the aggregate and it will result in cracking. Right. This gel that forms, how do they do it? The mechanism, actually alkali silicate gels, which the active silica and the alkali in cement they form, they attract water and they absorb them also by osmosis and tend to increase the volume. So, this gel, because it is a gelatinous structure, by osmosis it can bring in water, and it can the water can come in and it can absorb the water as well, and thereby when it absorbs water it swells actually. So, increases the volume. This gel exerts pressure onto the surrounding paste, leading to expansion, cracking and disruption of paste. That is what we said. And the expansion is actually attributed to hydraulic pressure generated by osmosis and swelling pressure of the reaction product. Both hydraulic pressure of the process of osmosis takes place through membranes from side of higher concentration to the lower concentration. Like you find, if you have one side concentration is higher, another side concentration is less, there will be a pressure existing between the two sides. So this is also related to like diffusion processes. We talked about molecular diffusion in solution, they are similar. So osmotic pressure is related to that also. So osmosis can take place through this gel, and this can exert hydraulic pressure together with the swelling pressure of the reaction. So that all this actually causes expansion and therefore the cracks. The result is something like this, typical. This results in what is called map cracking. You can see this is from a real life scenario. Usually it will take place around the aggregate. So just below in the side of the aggregates, and then crack proceeds. So it starts from, if there is an aggregate, from the aggregate all around, at other places from the aggregate all around, because expansive pressure will go from the aggregate surface to the outward into the paste, and it generates, and finally this sort of map cracking results from, and this concretus pollen off finally. So alkali aggregate reaction can result in this map cracking. Now the fineness of the aggregate has got a role to play. If the aggregate is very fine, this cracks can be seen relatively early, but in large jar aggregate, for example in coarse aggregate, when this alkali aggregate reactive, potentially alkali reactive aggregates are there. If it is there in the coarse aggregate, it can take years, not even 5-10 years. Hirakud Dam is one such example where actually cracks came because of alkali aggregate reaction. So these cracks can come in the long run, and this is of course put you in a difficult situation. So alkali aggregate reaction takes place, and it gives rise to map cracking. First thing, this all occurs in presence of moisture, because gel has to absorb the moisture has to come inside. So if you can prevent moisture contact, no problem, the alkali aggregate reaction will not be there. Use of cement with low alkali content, less than 0.6% sodium oxide equivalent. We talk in terms of alkali content of the cement in sodium oxide equivalent, because this is actually actual sodium oxide content plus potassium oxide content multiplied by a constant around 0.685 or something like that. So this, because they are it's related to their own molecular weight and things like that. So we talk in terms of sodium oxide equivalent, 0.6% sodium oxide equivalent. So that's what it should be. Now blast furnace slag and also pulverized fuel ash, they reduce down this. In fact, they do contain alkalis, but fortunately those alkalis are in some glassy phases together, in some sort of form which do not contribute to alkali aggregate reaction. Both GBFS and PFA, that is fly ash or similar other material, pulverized fuel ash, they do have alkalis present in them, but those alkalis are in such form that they do not contribute to the alkali aggregate reaction. So what you are doing, whenever you add these materials, there is a dilution of the alkalis present in the cement. So total alkalis present in the cement is now relatively less. If you are using 50% GBFS, you are actually reducing the alkali content, the OPC component, by 50%, and that is what has been suggested. You use more than 50% in blended cement, use PFA more than 25% in blended cement, with the alkali content of the Portland cement should not be more than 0.3 kg, 3 kg per meter cube of concrete. Use of aggregate, most important, use of aggregate potentially not prone to alkali aggregate reaction. This is known traditionally. If certain aggregate has been used for many years and it did not show alkali aggregate reaction, then that can be used safely. But if somebody is using a new aggregate, then it has to be tested. It is not very easy. There are several tests including STM Mortar test to test the alkali aggregate reaction, potentiality of an aggregate. There are petrographic tests, you look under microscope the presence of opal, etc., but they are not 100% foolproof, right. So, this is one issue. One would like to make them 100% foolproof as much as possible by all tests and see that that particular no traces of such material is there, and it's potentially the aggregate is not potentially alkali aggregate reactive before using it. New aggregates in dams, since aggregates are used locally or large industrial sites, even local aggregates you are using, because you cannot carry the aggregate from far off places. In such places, testing the aggregate for potential alkali aggregate reactivity is very important. There is a second variety called alkali carbonate reaction, not very often it is observed. This reaction takes place between certain dolomitic limestone and an alkali cement, and this has got also similar adverse effect as alkali aggregate reaction, right. Quite often it has been attributed to the clay minerals present in the dolomite. It is not very clear, not much research, and it is not very, it is a rare thing, it does not occur very often. This phenomenon is relatively less frequent and therefore not much has been done. In fact, this is quite often not well understood as well. So, this is all about the degradation processes that we wanted to look into this component of our lecture. So far, therefore, combining with the last lecture, the summary of the 2 lectures on durability, sulphate attack we have seen seawater attack and we have seen acid attack, carbonation and chloride ingress, carbonation and chloride ingress leading to rebar corrosion, that is what we have looked. We have discussed what is the corrosion process, and we also looked into alkali aggregate reaction. Now, all degradation processes are chemical degradation processes are by and large over. There is one physical degradation we will like to look into is the frost attack in our discussion, and then look into general strategy of general strategy towards protection against or durability enhancement of concrete. Now, important issue that I would like to highlight in the summary is that you see all places we have found that water is one of the major agent. Ingress of water is one of the major agent for all chemical degradation process to take place, and concrete must be sufficiently impervious to avoid such chemical degradation. I think with that we conclude this discussion. In the next one we will look into frost.